All right, so yeah, pretty much finish reviewing the exam. Okay, so probably tonight I will just kind of give out the final grade. Okay, and for this week lab. Okay, so make sure you rest for kind of the animal time. Okay, each person only has the 10 minutes. Okay, don't mix some kind of the time. Okay, so. Right, so yeah, if you have any question about the exam, okay, so yeah, you can come to my the office hour, okay. So I have one office hour, okay. So yeah, just after this lecture, okay. All right, so we need to continue chapter no today, okay. Yeah, we're gonna vote here on Wednesday, okay. So yeah, in Wednesday class, okay. So yeah, make sure you come in Wednesday class, okay. We decide kind of whether we stick on kind of the smart work or kind of switch back to the paper-based kind of responders, okay. So yeah, the future kind of exam quiz style, okay. So yeah, make sure come into kind of the class, okay, on Wednesday, okay. Yeah, we vote on Wednesday, okay. All right, okay, so if there's no further question, we continue chapter 11, okay? So for chapter 11, last time we talked about kind of mechanism 3, okay? So that's all about kind of hydroboration oxidation reaction, okay? So for this reaction, very unique kind of the property. First kind of the residual chemistry is kind of anti-Markovnikov, okay? So yeah, any question about exam, okay? Come to our office hour today, okay? So we have our office hour kind of after the lecture, okay? Yeah. All right, okay. So yeah, if you have further question, okay, just type in the chat window, okay? All right. So for the mechanism 3, okay, so the oxidation, hydroboration oxidation reactions, okay, so the residual chemistry follow anti-Markovnikov rule, okay, and so all right. Chapter 11, okay. Chapter 11 question also come to kind of after the quiz, after the lecture, okay. Officer, okay. Yeah. All right, okay. So stereochemistry, okay. This one follow kind of the thin addition, okay. So that's kind of different from the mechanism 2, okay. All right. So just give you guys kind of some idea, okay, what's going on. For example, okay, so yeah, we have this arcane, okay. So we do hydroboration oxidation reaction, okay. So remember first, okay, so yeah, we have boron, okay, and then second kind of the sodium hydroxide, okay, with the hydrogen peroxide, okay. Right. So once the reaction is done, okay, so we generate kind of something like this, okay. All right. Hydrogen goes kind of carbon with more the alkyl group touch, okay, and then OH goes kind of the internal terminal kind of carbon, okay. All right, and so why is that case? So why it has kind of a very unusual residual and also the kind of stereochemistry case. So reason for that kind of we learn this both the residual and the stereochemistry together by its mechanism, okay. So first case we have the boron will come in, okay. So boron is kind of structure like this, okay. And so you can treat the boron as some kind of metal, okay. So metal normally has kind of the weak electron withdrawing, low electron negativities, okay. So it has kind of partial positive charge, okay, and then the hydrogen has kind of partial negative charge, okay. So that's the different from kind of the hydrogen species we learned before. Previous kind of like water or some acid, okay, hydrogen kind of the negative positive charge, okay. All right, and then when it's kind of interact with kind of the arcane, okay. Right, so for arcane itself, okay, so under certain kind of induced condition, also spectral kind of the electron move around, okay. So yeah, most time kind of you have positive charge in the internal carbon and then partial negative charge on kind of terminal carbon because the internal carbon cation more stable, okay, second carbon cation more stable than kind of primary, okay. Right, and then when the boron comes in, okay, so because of the electron kind of interaction, electron effect, okay. And then we have So later, okay, so yeah, we come out later, okay, so questions, okay. Right. Negative, positive, okay. So the charge are matched, okay. So yeah, positive like negative, negative like positive, okay. So that's one reason, okay. So yeah, the charge match, okay. So most stable katakana, okay. A second reason kind of stereo hindrance, okay. So normally kind of the boron part kind of pretty big, okay, and then the hydrogen part kind of very small, okay. So in this case, boron part kind of the only access to kind of the terminal carbon, and no access to kind of internal carbon, okay. But hydrogen has no problem. Hydrogen kind of the extend out, okay, and then right afterwards, okay, and then yeah. We generate some kind of this squared kind of intermediate, okay. Should be kind of a transition state, okay. So right. So now you can see why it's kind of thin addition, okay, because the boron hydrogen, okay, so this one should be called hydride, okay, and then boron, okay, add on the same side of that bond, okay, and then that's why it's thin addition, okay. And eventually, okay, you generate kind of this kind of intermediate, okay. And certainly you can add another arcing to the boron, okay, so because there are kind of two actual hydrogens, okay. And then continue, okay, so and then eventually, okay, so that's first step, okay, hydroboration, okay, and then next step, okay, so just oxidation, okay, oxidation pretty much kind of just cleave off the boron, okay. We use the hydrogen peroxide and also sodium hydroxide, okay. So yeah, different from kind of the oxide mercuration reduction reactions, okay. So when you cleave off, okay, one mass without stereochemistry, okay. So yeah, the OH group is still on the same positions, okay. So that's the overall mechanism, okay. So make sure you understand this, okay, because this is kind of required mechanism, okay. Right, two reasons, yeah, kind of the most stable compound, second kind of stereo hindrance, okay. So we can show kind of the cartoon showed here, okay. So we are boron BH kind of the big, okay. So that's why it has kind of far away from kind of the most active carbon, okay, and go kind of the last active carbon, okay. Right. And in this case, we can actually kind of the comparative with that's the third way how do we make it alcohol, okay, and then what's on the top, yeah, hydrogen peroxide, okay, H2O2, okay, hydrogen peroxide, okay, that's oxidation reaction, okay, so that's what we call kind of the hydrogenation oxidation reaction, okay, yeah, all right. Okay, so next kind of won't be this be SN2. This is not SN2, okay. So SN2 reaction is kind of the substitution reaction, okay. So you didn't substitute anything, okay. So that's we call addition, okay. Yeah. This final step, okay. So looks like the substitution reaction, but reality should be kind of oxidation reaction, okay, because you can see this carbon, okay, increase kind of carbon number, so we generate kind of we know that kind of increase carbon numbers, increase oxygen number, increase oxygen number, that's called kind of oxidation reaction, okay. So mechanism different from kind of SN2. SN2 kind of something coming here, okay. So for mechanism, how to clarify kind of the BH2, okay. So that's not required, okay. But definitely kind of not SN2 reaction, okay. All right. Okay. So yeah. So here we can summarize the kind of the arcing reaction convert to alcohol. Okay. Right. So we learned the three arcing reactions. Okay. So addition reactions. Okay. Convert to alcohol. So the first one, remember, kind of the acid catalyzed kind of hydration. Okay. Right. So that's the acid. Okay. Right. So for this reaction, okay. So we follow Markov-Nikodym rule. Okay. So we have hydrogen goes kind of the terminal carbon and OH goes kind of internal carbon, okay. So because there are kind of no stereochemistry, okay, so that's why we kind of put a curved arrow, okay, a curved kind of bond, okay. And then the second way we learned kind of we call it the oxide mercuration reduction reactions, okay. So yeah, it's two-step reaction. The first step kind of so yeah, the mercury acetate, okay, and then second case, so yeah, sodium hydroxide, okay, so with sodium boron hydrate, okay. So keep in mind, okay, from this chapter, okay, so yeah, reaction condition can be very quite complicated, okay. So yeah, you have to memorize all the reagent, okay. So for the oxymercuration reduction reactions, okay, so you generate kind of same the product as the acid catalyzed kind of the hydration reactions, okay. Both have no stereochemistry, but follow stereochemistry follow kind of the anti-Markov-Nikodym flow. Hydrogen goes kind of carbon with more hydrogen attached, okay. Right, and then the last one we learned today is kind of the hydration oxidation reactions, okay. So yeah, BH3, okay. And then 2 is the So H2O2, okay, NaOH, okay. Right, so for this one, okay. So the different from your previous two, okay, so this one we generate kind of anti-Markov-Nikodym product, okay. So yeah, OH goes kind of terminal carbon and hydrogen goes kind of internal carbon, okay. And then this one kind of syn addition, okay. Yeah, that's here the keep in mind, okay. The first one kind of worst one because first one has kind of the rearrangement and also poor yield, okay. And then these two, second one and the third one kind of recommended, okay, because that's higher yield, okay, and also you can control the positions, okay. Right, and then here's some kind of just example for the kind of stereochemistry, okay. So yeah, for stereochemistry, okay, so you can add the OH and hydrogen from top of the double bond or from bottom, okay. So in this case, for the hydrogen oxidation reactions, okay. So yeah, also generate kind of a pair of enantiomers, okay. So yeah, that's showed here, okay. So one compound right showed here is kind of the add from bottom, okay, and another compound kind of the add kind of from top, okay. Another the enantiomer kind of hydrogen OH add from bottom, okay. And give you guys kind of more example, okay, about the stereochemistry, okay. So this time I use kind of the symmetrical arcing as example, okay. Right. So if I do kind of the hydrogenation oxidation reaction, okay. So yeah, you can write here just boring or kind of the boring P plus kind of THF, okay. So that's both the same thing, okay. Hydrogen peroxide and the sodium hydroxide, okay. All right. So once you're done, okay, so the OH and hydrogen can add from same side of double bond or kind of from outside, from kind of the top or from bottom, okay. So in this case, you generate kind of a pair of enantiomer, okay. All right. So this one OH and hydrogen add from the top, okay, and also you can add from bottom, okay. Yeah. So the relationship between these two are kind of a pair of enantiomer, okay. So mirror imaging kind of cannot overlap to each other, okay. And so if you do a similar reaction, okay, for the other two reaction conditions, okay. So yeah, you will get kind of all the full possible product, okay. So for example, yeah, here you do kind of as catalyzed kind of hydration reactions, okay. So for this one, okay, actually kind of because there are kind of no stereochemistry, okay, and in this case, yeah, you can have both the syn addition and also anti-addition product, okay. So we draw syn addition product first. And if you like, you can design R and S, okay, for all the stereocenters, okay. Right, so that's syn addition, okay, and anti-addition I draw here, okay. OH. Right, so anti, okay, so you can also have two, okay, so one kind of OH, the dash bond, and then hydrogen kind of the wedge bond, okay. Another is kind of the OH kind of wedge bond, and then hydrogen kind of dash bond, okay. All the possibility, okay, yeah. All right. Okay, so that's just something keep in mind, okay. So we learned 3 ways to convert arcing to alcohol, okay. So yeah, you have to understand their kind of stereochemistry and regiochemistry, okay, and then their kind of reagent, okay. So that's something keep in mind, okay. So all three, okay, based on 3 different mechanism 1, okay. So yeah, the acid catalytic kind of hydration, okay, based on mechanism 1, okay, and then yeah, the oxymercuration based on mechanism 2, okay, and then hydrogenation oxidation based on kind of mechanism 3, okay. So yeah. All right, and then yeah, remember, okay, so in the oxymercuration reactions, okay, so we can also do kind of the alcohol addition, kind of water addition to kind of alkene, okay, CH3 bond, okay, and then we generate kind of ketone, okay. So actually, we can do the similar reaction for the kind of the alkyne, just use kind of hydrogenation oxidation reaction conditions, okay. So yeah. So that's really come to kind of the what kind of alkynes, terminal one or kind of internal one, okay. So if it's kind of internal alkyne, okay. So CH3 bond, okay. So that's you give kind of ketone, yeah, same as kind of the oxymercuration reactions, okay. All right. So give you one example, okay. All right, so we have this alkyne, okay. All right, and then we apply kind of same reaction conditions, okay. BH3H2O2, okay, NaOH, okay. All right, so once the reaction done, okay. Yeah, that's got ketone, okay. All right, for you guys, okay, so if you cannot draw the product in one shot, okay, so yeah, what you can do is kind of try to kind of draw the ketone product, okay, yeah, same like the oxymercuration reactions, okay, so yeah, the generate kind of ketone, okay, eno, okay, and then generate eno, okay, and then yeah, you use the kind of eno convert kind of to ketone, okay. So pretty much yeah, like this, okay. So you generally kind of add hydrogen and also the OH onto kind of this CH3 bond, okay. So yeah, let's do kind of thin addition product, okay. It doesn't matter, okay. So because it's kind of symmetrical ketone, okay. Actually, kind of once it's done, okay. So yeah, let's maybe put the OH here because generally kind of the OH on the left. Okay. Right, but doesn't matter, okay. So because this kind of symmetrical one, okay. Right, once you're done, okay, so yeah, just keep in mind, okay, so yeah, CC double bond become kind of CC single bond, okay, and then carbon with OH attached, okay, become ketone, okay. Yeah, that's the case thing, okay. So yeah, remember how do you draw the kind of the product here, okay. So that's the internal alkyne, okay. So internal alkyne, okay. So if you use kind of the hydrogenation oxidation reactions, okay, give kind of ketone, okay. And for the terminal alkyne, okay. So for terminal alkyne, remember for the oxymercuration reactions, okay, also give kind of ketone, okay. But yeah, for the hydrogenation oxidation reactions, okay. So yeah, that's you give kind of the different compound, okay. So aldehyde, okay. The reason for that kind of that's for the kind of anti-Markov-Nikolov rule, okay. So generally kind of hydrogen goes kind of internal carbon and OH group to kind of terminal carbon, okay? And then terminal carbon become kind of CO double bond. That's aldehyde, okay. Right. And then just see also another different things kind of if you try to do the hydrogenation oxidation reaction for the terminal alkyne, okay. So you cannot use kind of the BH3 anymore, okay. Why that? Okay, so just kind of give you quickly one example. So that's your terminal alkyne, okay. So if you use the BH3, okay, because they're kind of the tree bond are kind of two double bond, okay. So in this case here, the pretty much they generate something like this, okay. You add a pair of the BH3 onto kind of the compound, okay. So that's just no reaction, okay. So if you click okay, turn kind of diol cannot kind of extremely unstable, okay. right? So to avoid this kind of situation, okay, people use kind of a special reagent for this reaction, okay, called kind of the diacetylamyl kind of boron, okay. So here, okay. So diacetylamyl, okay. So questions, okay. Yeah. So here's kind of the mechanism 3, okay. So for the kind of the alkyne addition, okay. Yeah. So here we just suppose use kind of hydrogenation oxidation reactions, okay. Yeah. Mechanism 3, okay. All right. So we cannot use kind of regular kind of the boron, okay. So in this case, yeah, people use kind of the diacetylamyl kind of the boron, okay. Diacetylamyl boron kind of structure like this, okay. So pretty much yeah, I can see kind of just here the two, yeah. Two, how do we call that kind of, yeah, 1,2-dimethyl iso 1,2-dimethyl propyl group, okay, 1,2-dimethyl propyl group, okay. You have 2, okay, and then just here the only one hydrogen bound to kind of this boron, okay. So you see kind of, yeah, let's see a very bulky structures, okay. And in this case, okay, so yeah, when you do the addition reactions, okay, so you can only add the one boron on it, okay. So yeah, pretty much yeah, you hydrogen and then B, okay. So trying to kind of something like this, okay, because yeah, this one too bulky, you cannot add a second kind of this here that's the amyl kind of boron reagent, okay. So reaction can stop here, okay, and then yeah, you apply some kind of oxidation reaction conditions, okay. That's you cleave off kind of the boron part, and then you generate kind of its corresponding kind of the alcohol, okay. So also kind of enol, okay. And then this enol can quickly totalize into kind of the aldehyde, okay. So eventually, okay, so you generate kind of the carbonyl, okay. It's aldehyde, okay. So in other words, okay, so yeah, summarize here, okay, so yeah, if you use internal alkyne, okay, so you generate kind of ketone, okay, so that's the same as kind of oxymercuration reduction reactions, okay. But for the terminal alkyne, okay, so you have to use special reagent called kind of diacetylamyl kind of boron, okay, and then you generate kind of aldehyde, okay. All right, so to further to compare these two, okay. So we do a little bit of practice, okay? Little bit of practice, okay? All right, so we have this kind of terminal alkyne, okay? And then try to draw the kind of the product here for these two conditions, okay? Right. First one kind of the oxymercuration reduction conditions, okay? And then second one, okay, so yeah, we use diacetylamyl, okay? Diacetylamyl boron, and then with kind of the oxidation condition, okay? All right, take a try, okay? Try to draw the product, okay? All right, keep in mind, okay, so far, yeah, the reaction we learned kind of here, kind of just here, eventually, yeah, the first convert kind of alcohol if you cannot draw the product, okay, but yeah, if you can directly draw the product, that's be fine, okay, but yeah, if you cannot draw it directly, okay, so yeah, do it stepwise, okay. Yeah. All right, take a try, okay, try to draw the product for these two reactions, okay. All right, keep in mind, okay, so yeah, pretty much we just generate kind of alcohol, okay, add water onto kind of CC3 bond, okay, and then you first generate kind of enol, okay, and then fall into kind of the enol total, enol keto tautomization, okay. give you kind of the aldehyde or ketone, okay. All right, so let's me work on this, okay. So remember we add water, okay. So just the most important kind of where OH goes, okay, and then where hydrogen goes, okay. So for the oxymercuration reactions, okay. So hydrogen goes kind of terminal carbon, okay, and then OH goes kind of internal carbon, okay. So that's the case in case. So oxymercuration reaction, okay. So we have still follow kind of Markov-Nikoddy through, okay, right, and then afterwards, okay. So that's pretty easy, okay. So this one can quickly tautomerize into kind of the ketone, okay. Yeah, that's the final product, okay. And then for the oxymercuration for the kind of the hydrogenation oxidation reactions, okay. So if you cannot draw the final product, you do the same thing, okay. So first draw kind of the addition product, addition water, okay. So here kind of difference is now the hydrogen goes here and then OH goes here, okay, because this one follow anti-Markov-Nikoddy, okay. And then you quickly draw kind of the ketone thermalization product, okay. So that's should give kind of aldehyde, okay. All right, anyone has a question, okay. So that's the hard part for this chapter, okay. So addition of the to alkyne, okay, really depends on conditions. You generate kind of different product, okay. So looks like no question, or maybe too many questions. All right. Okay. So now we moved on bunch of the oxidation reaction and also reduction reaction of the alkene, okay. Okay. So here we will learn kind of the full oxidation reaction, actually kind of 3 oxidation reaction and then 1 reduction reaction. Okay. So remember in the previous chapter, okay, so we learned that kind of the oxidation reactions kind of you decrease hydrogen number, increase oxygen number, okay. Reduction reaction you increase the hydrogen number, decrease oxygen number, okay. And here, okay, so we will learn learn 3 oxidation reaction one by one, okay. The first one is kind of the epoxidation, okay. So that's just one step you convert the alkene into kind of epoxide, okay. Right. And general reaction, okay. So showed there, okay. So I just also quickly draw you guys, okay. So the reagent use kind of the convert alkene to epoxide kind of we call it kind of percarboxylate, okay, percarboxylate, okay. So percarboxylate has this kind of structure, okay. Right. 3 oxygen, okay, that's called kind of percarboxylate, okay. So for the real structure, okay, so pretty much like this, okay. There are kind of 2 oxygen here, okay. 2 oxygen here, okay. So normally kind of carboxylate, okay, so we have kind of just the 1 oxygen, okay, so this is OH, okay, but percarboxylate kind of has 2 oxygen, like here the the oxide, okay. And once reaction is done, okay, so you generate kind of the epoxide, okay. So if I draw this case, so you should already understand that for the stereochemistry of these reactions, kind of thin addition, okay. Okay, so that's something keep in mind, okay. And the second thing, kind of that's probably the easiest way for us to prepare kind of alkene, prepare kind of epoxide, okay, from alkene, okay. So previously we learned another way is kind of halohydrin followed by SN2 reactions. Okay, so that's you need 2 steps. Okay, so remember, yeah, similar thing. Okay, we can do the halohydrin. Okay, so yeah, BH2. Okay, and Br2 water halohydrin reactions. Okay, and it doesn't matter. Okay, so here Br. Okay, and okay, halohydrin. Okay, so and then we do SN2. Okay, so apply a little bit of base. Okay, depolonate kind of OH group. Okay, and then that's here SN2 reactions. Okay, close to the ring. Okay, so eventually also get kind of epoxide. Okay. So that's the kind of hassle, okay, because you need 2-step reactions, okay. So the organic reaction, if you want to kind of the high efficient case, so you want the last possible, okay. So here we only 1-step reaction get everything done, okay. Yeah, that's the much better, okay. All right, and then so for the peroxide, okay, hydrogen, we call kind of the percapsicity, okay. So here, okay, so the what's the common percapsicity we can use, okay. So first one kind of the perbenzoic acid, okay. Yeah, if you guys have any questions, okay, so we are just here type in kind of chart window, okay. So perbenzoic acid kind of has this kind of structure, okay, pH, okay, so yeah, the phenyl, okay, and then so capsaicin should be kind of COH, okay, for the perbenzoic acid, okay, so we have kind of COOH, okay, yeah. And then second one kind of the called the per acetic acid, okay. Right. So acetic acid C3COH, okay, so yeah, for the per acetic acid, okay. Yeah, there's one extra oxygen here, okay. And the last one, and also the most important of the reagent, okay, so for the epoxidation case, so yeah, that's IMC-PBA, okay. So full name is kind of the I'm chloro perbenzoic acid, okay.
How do you spell the second one that you wrote?
Per acetic acid, okay. PERACETICACID, okay. Acetic acid, okay. Just P put the PER before the acetic acid, okay. Right. And then for this one, okay, so just add the I'm chloro before kind of benzoic acid, okay. So the per benzoic acid that will be kind of the new reagent now. Okay. So I'm chloro per benzoic acid, okay. So I'm CPBA, okay. So that's the one of the very famous reagent kind of the in the organic chemistry, okay. So as long as people mention kind of how do we make kind of the epoxide, okay. So 90% time kind of people recommend kind of MCPBA, okay. So that's the very unique one. I don't know why, okay. So so looks like the benzoic acid should be kind of cheaper, okay. But normally people kind of just use kind of per chlorobenzoic acid. I don't know why kind of cannot use kind of the paro chlorobenzoic acid or also chlorobenzoic acid, okay. So just kind of make it. I guess probably the starting is kind of cheaper, okay. So that's why kind of the chlorobenzoic acid, okay. So it's structured like this, okay. A chloro, okay, and then per chloro, okay, and then and benzoic acid, okay. Oh, per chlorobenzoic acid, okay. Right. And for this reaction case, mechanism actually kind of not required, okay. But if you guys have interest, I can quickly show you what's going on, okay. Right. So we have kind of the arcane, okay. Right. and then we have kind of the per capacity coming in, okay, and then that's here show like this. So that's here the per capacity, okay. Right, and then you shift the electron bunch, okay, so yeah, first kind of the lone pair electron on this oxygen, shift to here, okay, and then the shared CC bond kind of electrons, okay, and then goes also these carbons, okay, so you build up kind of triangle, okay. Meanwhile, okay, so this the shared electron between two oxygen shift to kind of carbon oxygen, and then shared electron between kind of carbon oxygen shift here, pick up the protons, okay, and eventually kind of there's the shared electron between oxygen and the hydrogen, okay, gives kind of oxygen here, okay. So you shift the electron kind of like 5 times, okay, eventually, okay, so yeah, break up here this oxygen and then you generate kind of should be kind of epoxide, okay, single bond, okay. And then another product just of regular the capsaicin, okay. Yeah. So that's the whole reaction mechanism, okay. So this is not required, okay. But just let you know why it's kind of thin addition, okay, because you add kind of oxygen kind of over the CC bond, okay. All right, and when you draw the product, okay, so give you guys kind of a couple of examples, okay. So because kind of thin addition in this case here, normally speaking, kind of you generate kind of a pair of enantiomers, okay. So depends kind of what's arcane, okay. So if it's kind of unsymmetrical one, okay, so definitely kind of generate kind of the pair of enantiomers, okay. But for the symmetrical one, okay, so that's maybe you guys can take a try, okay. So let's try finish this one first, okay. So MCPBA, okay, so react with kind of this arcane, okay. So after reaction, we generate kind of a pair of enantiomers, okay. So one is kind of so epoxide oxygen, the connect by the dash bond, okay. So that's dash line, okay. So that's also dash line, okay. Another one is a kind of enantiomers, okay. Oxygen connect by wedge bond, okay. Yeah, so that's it. So just you can add the oxygen from the top of the bond or from bottom one, okay. So that's why generate kind of a pair of enantiomer, okay. And then you guys can take a try, okay. Yeah, try to draw the kind of the product for these two arcane. One's kind of the cis and one's trans, okay. Try to draw all the product, okay, and then determine their relationship, okay. Bond movement for the first mechanism. Yeah. So for this one, okay, the bond move kind of actually not required, okay, but if you guys want to clear see it, okay, so yeah. So this lone pair electron on oxygen, okay, goes to here, okay. So that's here, okay, this bond, okay. And then maybe different color, okay. So this pi electrons, okay, goes pick up kind of oxygen, okay, and then that's these two. Okay. Right, and then these two, okay. Oxygen shared electrons, okay, so these two, okay, so goes here, okay, so that's generate kind of another pi bond between the kind of the carbon oxygen, okay, and then this one, okay, carbon oxygen electrons, okay, so pi bond shift to here, okay, and then build up an oxygen hydrogen bond, okay. Actually that's this bond, okay, oxygen hydrogen bond, okay, that's from here, okay. And then last kind of this oxygen hydrogen kind of bond, okay, all give kind of the oxygen here, okay. So you generate kind of lone pair electrons, okay. So try just draw like two circle, okay. Yeah, so that's here the old bond movement, okay. So a little bit complicated, okay, but here the yeah, not required, okay. All right, so we come back here still to these questions, okay. Yeah. So that's not required, okay. So we are just here a little bit of keeping idea. That's enough, okay. All right. So for this one, okay. So yeah, again we can draw a pair of enantiomers, okay. Yeah. So that's here the yeah. Because the starting matrix kind of yeah trans, okay, so after the approximation, okay, so also generate kind of transport that, okay, so that's a single addition, yeah, property of single addition. Single addition you generate kind of same stereochemistry, okay, as kind of the yeah starting material arcane, okay, so trans still are trans, okay, but for the case, okay, so yeah the yeah actual reality we only generate kind of one product, okay, yeah. The reason for that kind of yeah, some people say kind of yeah, both methyl can be the dash or both can be veg, okay, but yeah, the reason for that, yeah, these two actually kind of same compound, okay. Yeah. So that's we call kind of yeah, you flip the molecule 180 degrees, okay, so you that kind of the kind or yeah, superimposable with another the molecule, okay. So this actually we generate kind of a pair of a methyl, okay. Yeah, kind of a methyl compound, just the same compound, okay. On the top, yeah, actually kind of a real enantiomer, okay. Yeah, that's the other another hard part for this chapter, okay. So you should not only able to kind of draw the old product, you have to determine their relationship, okay. Okay, so that's the first oxidation reaction, okay, and then we move to second one, okay, called hydroxylation reactions, okay. So hydroxylation reaction, okay. So for hydroxylation reaction, actually kind of pretty easy, okay. So yeah, you apply some reagent, okay, and then just add the 2 OH onto the 2 carbon on consist bond, okay. So yeah, you generate kind of die, okay. And then general reaction actually I showed already on the kind of screen, okay. So yeah, you have kind of arcane, right, and then. So the reagent for this reaction actually kind of we use called kind of osmium tetraoxide, okay. OS, okay, that's osmium, okay, and then tetraoxide, okay, so 4 oxygens, okay. After the first step, okay, and then second step, okay, you use kind of sodium kind of sulfite, okay, so keep in mind, okay, not sulfate, okay, sulfite, okay. So SO3, okay, sodium NO2 SO3, okay, not SO for SO4 has nothing, okay. SO3 you can reduce kind of product, okay. So yeah, first intermediate into kind of final product, okay. So this is the reducing reagent, okay. And then after reactions, okay, so you generate kind of die, okay. Yeah, like I mentioned, kind of in this chapter, there are kind of a lot of reagent, okay, a lot of reaction conditions, okay. So yeah, sometimes kind of easily get confused, okay. So yeah, sodium sulfide, okay. All right, so that's the one reaction conditions can be used, okay. So another one, okay. So yeah, we can use the potassium hydroxide, potassium permanganate case, and with the sodium hydroxide, okay. Yeah. So this one can also convert arcane to kind of die, okay. So that's why remember in the previous chapter, okay, we talked about kind of the alcohol oxidation, okay. So we prefer use kind of the chromic acid or kind of the sodium bichromate, okay. So yeah, chromium kind of reagent, okay, not use kind of the potassium the permanganate, because potassium permanganate kind of the no selective, okay. So yeah, if there kind of the C bond, C3 bond even, okay, can oxidize, okay. So yeah, convert kind of to some die, okay. So yeah, all right. So that's the And so third one, okay, so these two kind of if you want carry reaction, you have got kind of 1-to-1 equivalent kind of region to the starting material, okay. But the third one, you can use catalytic amount, okay, so that still we still use kind of osmium kind of tetroxide, okay, OSO4, okay, and then we add some kind of oxidation region, okay, so T-butyl hydroxide, okay, hydroperoxide, okay, so it's actually kind of T-butyl hydroperoxide, okay, so that's here the oxidation region, okay, so once this one get onto kind of from kind of the intermediate, okay, you cleave off, okay, and then kind of this one oxide kind of osmium kind of back to kind of osmium tetro oxide, okay, so that's kind of can be reused, okay, so because the osmium tetroxide kind of a little bit toxic, okay, so normally you don't want kind of use too much, okay. And for the magnesium, okay, so for this reaction actually can also not required, but just quickly show you guys what's going on, okay. So for this reaction, okay, keep in mind, okay, so stereochemistry also syn addition, okay, so that's maybe I write down here, okay. That's kind of important, okay. Because you kind of the OH group add onto the same side, okay. So why is syn addition, okay? Because osmium tetroxide coming in kind of from same side of the bond, okay. All right, so that's osmium tetroxide, okay. And the shift of the bond, okay, so this bond, okay, shift to here, okay, and then this double bond, okay, shift here, okay, so you build up kind of two CO bond, okay, so one goes here, okay, and then one goes here, okay, and then afterwards, okay, so you generate kind of something kind of like this. There's a lone pairs on osmium, okay. Yeah. So somehow like the 5 membrane, okay. And then you apply kind of sodium the sulfide, this guy, okay. And then that's cleave off, okay. So the osmium, okay. So we cleave off here, from here. So that's give kind of the die, okay. So that's why it's kind of syn addition, okay. Okay, so for you, okay, so you don't need to memorize all the mechanism, okay. So most important thing kind of you need to know how to draw the product. That's the key thing, okay. So and also memorize what's reaction, okay. So quite often happen kind of student get confused, okay. So mess up kind of the old oxidation reaction conditions, okay, and remember kind of the wrong region, okay. So that's something you have to the little bit keep in mind, okay. So here's kind of make sure you see kind of the osmium, okay. Osmium that means kind of die, okay. 2 alcohol, okay. Right. Once reaction is done, okay, syn addition, okay. So for this reaction, okay, we also try to kind of a pair of the enantiomers, okay. So one we have kind of 2 OH at from the top, okay, and then another one, okay. So we have 2 OH add from bottom, okay. Yeah, so that's a pair of enantiomer, okay. All right. Let's see, okay, so Yeah, we'll study all the analysis kind of in the next class, okay, because we're already 50, okay. All right, do you guys have any questions? Let me see. Question next to which maybe okay. So yeah, we should finish the chapter 11 kind of on Wednesday. Okay, so definitely can finish. Okay, not too many material left. Okay, and so we can have kind of quiz either on Friday or maybe Sunday or Saturday. Okay, but if you guys really like more time to prepare, okay, I can push to next Monday. Okay, so we can talk about this one on Wednesday. Okay, so in this case, coming kind of Wednesday class. Okay, so average or exam. Okay, so exam. Okay, so far. Okay, so I almost finished kind of review exam. Okay, pretty good. Okay, so at least like 72, 73 something. Okay, that's pretty good. Okay, so I will say okay, 72 or 73 kind of the percentage. Okay, so once I finish kind of go through exam tonight. Okay, so I will send out the email. Okay, and tell you guys kind of what's the average of the exam. Okay. Yeah, on Wednesday, okay, please come into the class. Okay, so we need to decide kind of whether we stay on kind of the smart work for the online exam or kind of go back to the paper-based. Okay, use kind of respondents. Okay, and also probably Wednesday we'll also decide kind of whether we have kind of quiz on Friday or maybe push to kind of on Saturday or Sunday or even Monday. Okay. There will be no curve for individual quiz or exam. Okay. So if necessary, I will do the curving for the total grade, final total grade, okay, like we did kind of the in Uganda Country 1, okay. Yeah, no curving for individual exam quiz, okay. Mm-hmm. Yeah, that's true. Okay, so so normally speaking, kind of for some reaction, okay, so I like to kind of show the movement of the bond, okay, but sometimes kind of things get kind of more complicated, okay, so if necessary, I will show kind of movement bond, okay, so some simple one, okay, so for this one, okay. So shift electron kind of like the 5 times, okay. So that's a little bit too much for you guys, okay. So this one actually kind of you just memorize kind of the reaction product, okay, and then understand the kind of single addition. That's enough, okay. So it's not necessary kind of then the mechanism, okay. So for some reaction like the hydrogenation oxidation reaction, okay. So probably I will show you kind of the movement bond between mechanism, okay. That's help you kind of understand the why is the anti-magnetic, okay, and also the white kind of single addition, okay. So but if you have interest kind of definitely kind of show you kind of movement bond, okay. So actually kind of for all the mechanism kind of explain kind of also in your book, okay. So if you still don't understand, okay, so please come to my office or kind of or kind of look at the book, okay. So but for some kind of mechanism I said kind of required, okay. That means kind of I will testing kind of in exam quiz, okay. So that's you have to learn how to draw it, okay. So not required, okay. So that means kind of I won't test kind of exam quiz, okay. Right, no problem. Thank you.